Hi, everyone. Today we're going to be talking about active learning modules for math and chemistry. I'm Jordan Hassler, and Jason Sonnenberg is here with me today. So we'll get started here by taking a look at how we can use Wolfram Alpha Notebook Edition to do active learning exercises. So one of the first things I want to talk about today was fractions, and then we're going to see how we can visualize those. We're going to see how we can use Notebook Edition to compute those. And then we're going to see how input and output predictions can allow us to compute various other properties, such as finding the numerical value of a fraction. So we'll start by taking a look at adding 1/4 plus 2/4. In Notebook Edition, you can just press enter, and then that will compute the answer for you. So we find that the answer is 3/4 here. And I wanted to point out, we'll also be talking about how you can get the step-by-step solution and then various other computations. So we can also have a different way of writing this. So we don't have to say add, we can just say 2/5 plus 4/5 and then press enter here. We find the answer is 6/5. And then if we notice here, there's this input output suggestions here. So on this output 6/5, we can get the numerical value. So I've already have that here, but I can show what this does here. So we press that and we get that 6/5 is approximately 1.2. We can also simplify fractions that are symbolic in nature. So we can do simplify a over b plus c over b. We find a plus c over b. We can do fractions with different denominators, 2/3 plus 3/4. We get 17/12. We can do another example, 3/4 plus 1/6. Again, we can get that numerical value by clicking on this, and that will output the cell of 11/12 with the numerical operator applied here. So we find the answer is approximately 0.916 repeating. We can combine fractions that are as general as we want. So a over b plus c over d. Those combine to give us ad plus bc all over bd. Not only that, but in Notebook Edition, we have the power of Wolfram Alpha to show the steps here. So if we type in show steps 2/3 plus 3/4, then we'll find that this step-by-step solution pod appears here, and we can click show next step and show one step at a time. How does it compute out? Or we could click show all steps, and that will just show all those remaining steps there that that would allow us to compute out the answer of 17/12 here for when we add these two fractions. Not only that, but we can get visualizations in Notebook Edition. So we can make a pie chart of our problem here. And here we see a pie chart representation of adding 1/3 and 1/3 and getting 2/3. We can do the same thing with fractions with different denominators here. So we see our representation of 2/3, our representation of 3/4, and then a representation of our answer for 2/3 plus 3/4. We can get a more symbolic version with a manipulate. So if we just type in pie chart x, y, z with varying x and y, where x and y represent the angle of our sector here. So we can vary x and y, and we can see our representation using a pie chart. Not only that, but we can also see our fraction representation on a number line. So if we just type in line plot of 2/3, 3/4, then we can find a representation of those 2 points on a number line. And we can see here that, for instance, 3/4 is larger than 2/3. We can also get the location of the summation of those two, which is represented here on the number line, and we can see that the sum of the two fractions is greater than either fraction there. Not only this, but we can also get information on solving proportions and fractional algebraic equations. So we can type in solve 4 over a is equal to a over 4 for a greater than 0, and we can find that positive value that makes that true. And then you can verify that 4 over 4 is equal to 4 over 4. We can also solve more complicated versions. And again, we can either specify that we want to solve on a particular domain, or we can solve in general here. We're also going to be talking about, next, we're going to be talking about fitting data to a line. And I'm going to show a mathematical example, and then Jason also has examples of using data and data processing for chemistry. So we can recall that 2 points determine a line. So if we have the point 2, 3 and 5, 8, in notebook edition, we can evaluate this. So we have this natural language input here of the line for 2/3, 5/8. Then that's interpreted as the Mathematica, the Wolfram Language expression infinite line of 2/3 and 5/8 here. And then once we have that, we can figure out more information about that. For instance, we can take the last output there and do graphics of that. And we're going to find this line representation here in the form of a graphic. One activity that is commonly seen in both your Algebra 2 classes and your chemistry and biology classes is you have a set of data, and then you want to collect that data and then process it. So we can define variables in Notebook Edition. One such way of defining a variable is to use the notation set, and then the name of what you want to call that. So for here, I was going to call this data, and then you'll input your list of data here. So we have this list of lists, and this represents our various points that we collected. We can evaluate that. Once we have evaluated that, we can find out more information on that. Again, we have this output predictions here. And one such suggestion that we can do is we can fit this model. We can fit a model to this data. So we have this set of data here, and then we can click this button here, and it's going to output what we have here. So you'll get this linear model fit of data with the specified variables. Again, with various data fitting functions, some of your points will be above the line, some can be below the line, and in general, you'll have both. So we find that when we apply a linear model fit, we get the equation 1.7176 times x minus 0.022825. Usually you want to find more information on the validity and accuracy of your data. So we can obtain information on various associated values here. So you can find adjusted R squared. And again, you can access all of this through the input and output suggestions. So for instance, if I evaluate this here, then I can obtain the various properties. I can obtain an analysis of variance, and then the various parameter estimates. So that's what I've done here. I've obtained this adjusted R squared. And we found the adjusted R squared was approximately 0.993251 here. We can also go to this and get a plot of the fit, which is what I've done here. So how I do that is I go here and click on this button here, the suggestion here, and that will produce this visualization here. We see our data, and then we see our linear regression model here. And then another suggestion that's provided is being able to get a table. So we can get the table of the analysis of variance, and that's been presented right here. So to summarize here, we can take our various inputs, we can define variables on those inputs, and then we can do various computations using notebook addition here to find out statistical models and information. One other thing that that Wolfram Alpha notebook edition is quite useful for is being able to solve equations. So in your Algebra 2 classes, and even Algebra 1, you'll use various identities and properties to be able to solve equations. So one of the tools that's useful for this is our various definitions in algebra. So we learn about additive identities. We learn about additive inverses. So in notebook edition, you can get information on those. So we can type in additive identity definition, and then we get a summary of what this means. So essentially it means if we add 0, it's not going to change our answer here. So we have our equation here. One such equation that we might want to talk about is a linear equation. So how can we solve a linear equation such as 2x plus 3 equals 5? So we can just type this in to notebook addition, or 2x plus 3 equals 5. We could do what we did earlier and get a step-by-step solution, but we might want the students to be able to, in an active learning environment, figure out how can we solve this equation. So we can just say, let's add 5 to both sides. Once we do that, we're going to see that it's interpreted as this Wolfram Language function here, add sides. So what did it do? It added 5 to both sides here. We see that when we added 5, we got 2x plus 8 equals 10. So in a certain sense, this has made the equation more complicated to solve. So we said before that we had this additive identity, and we want to add something that's going to make the equation simpler. So we want to be able to add something to both sides that's going to make our equations simpler. So we set that back to 2x plus 3 equals 5. Now, what if instead of adding 5 to both sides, I had added -3 to both sides? Well, we can see what that does here. So now notice that, so we've added -3 to both sides of our equation, and now we have the equation 2x equals 2. So we notice that there's 1 fewer terms here. And then the students can then explore, well, what would happen if I multiplied both sides by the same number? Is that going to make things simpler or not? So the key point here is we're trying to solve for a particular value of x. So now that we have got to the point 2x equals 2, well, we could try dividing both sides by something to try to get the x variable on one side and the numeric values on the other side. So if we divided both sides by 2, the Wolfram Language function here can do that, and we get x equals 1. Now that we have this equation, how do we know this is actually the answer? Well, we said that the equation was 2x plus 3 equals 5. We can verify that now. So we have this a function. We have the ability to verify this in the Wolfram Language. So we can use this natural language input here of, well, evaluate, and then the equation at a particular point. And once we do that, it's interpreted as this replacement rule here. So we find that we obtain the answer of 5, which is what we, which was the right-hand side of that original equation. So we can verify, and indeed the answer here was 1. We can work with more complicated algebraic expressions. So we can multiply both sides by a variable here. So we get, if we had this proportion 2 over a is equal to a over 2, well, let's multiply both sides by a and see what happens. We obtain this expression here. So all this means here is that we don't know from the very beginning that a is 0 or not. So when a is not 0, so if we make this assumption that a is not 0, we get 2 equals a squared over 2, and then we can work with that expression. So we obtain, after multiplying both sides by a, 2 equals a squared over 2. And now, again, we want to try to get the variable on one side of the expression and the numerics on the other side. So we can multiply both sides of 2 equals a squared over 2 by 2. We obtain 4 equals a squared. And then once you have that, you can solve for a. So we could type in, for instance, solve 4 equals a squared for a. And then we obtain -2 and 2. And again, if we had wanted to, we could go back and evaluate the formula at the given values, which would work the same way as in this linear case. So at this point, the students might be wondering, well, how did we figure this out? Well, again, we used various mathematical definitions, and we can also get those definitions again. So during these activities, we've seen that we're using multiplicative identities and inverses, and we can obtain our that definition as well. One other topic that students sometimes find difficult at first is solving quadratic equations. So today we're seeing how to solve this using the Wolfram language. Again, I want to point out that there are multiple ways of solving these. So there's quadratic equations, there's completing the square, and both of those are available for a step-by-step solution. So if you're wanting to work with the expressions, what makes notebook addition useful is that you can take your data and then perform more information on that set of data. So we could solve this equation. Then once you have that equation, you can get the numerical values again by this output suggestion here. You could get just the first solution if you would wanted. And there are other things you could do as well. You could set a variable using these output suggestions here. So if we numericize the roots, which in a math class, you might be more used to this symbolic representation here. And then in your science classes, you may prefer a numeric representation of those. So we can get the numeric representation by using the output suggestion here of numerical values. We obtain this cell here. This allowed us to numericize these roots. And we found -4.30278 and -0.697224. You can solve this in complete generality. And essentially, you're getting the quadratic equation here. You could also, at this point, click step-by-step solution. And that would give you the steps here. So if you forget how to solve quadratic equations or completing the square methods, you can obtain that information here. And this will show you how to do that. And again, we can also not only complete the square, but we could use the quadratic formula. And by adjusting this over here, we can do that and click show all steps, and it applies the quadratic formula for us here. Logs and exponents are more of a pre-calculus topic, an advanced algebra 2 topic. We can work with those as well, and can compute a list of logs if you wanted. Once you have that data, you could do other things with that data. Maybe you wanted to know what was the max of that set of logs you computed. You could click max there, and it would give you that it was 4. And you can in fact keep clicking output suggestions here and doing various other computations with that. You could get the binary form, for instance, if you wanted. You could set up an activity on computing the pH. So you could compute the negative log base 10 of 100. You could plot a pH curve. You can again define variables. So we don't have to say set pH. We could also say let pH equal. You could solve the pH for the hydrogen ion concentration. You can check your answers again. So that is logarithms. What's quite useful in Notebook Edition is we've implemented a lot of interactive visualizations. So as we talked about before, we have our identities, we have our zero product properties. So you get our definition here, and then you also get some advanced information if you're in a college advanced algebra class. Again, you can find zeros. You can solve by factoring. You can use the zero product property to get the solutions. You can plot a function with specified zeros. So if you have factored form, you can quickly read off where does zeros are going to appear. So -1, -2, -3. What's nice about this is that you can plot an equation in this form, and then for this visualization, you can see where those zeros are at. You can do things like, what happens if I squared one of the terms? So what happened in our graphic representation over here? You can see that it bounces off the axis here. You can see what happens if we squared a different term. It again bounces off the axis. And then you can see that it's below the axis in this case, and above the axis in this case. And then when you get to calculus, you can study things like continuity and intermediate value forms to be able to determine things like, well, which side of the axis am I going to be on? Where can it cross the axis, et cetera, et cetera. So you can do things like evaluating near a point and see is it positive or negative at that point. Again, plotting. What's really nice about Notebook Edition is that you can type in with varying A, B, and C, and it produces this manipulatable plot here, which is quite useful in that you can change the vertical axes, you can adjust your horizontal axes, you can explore what happens if I had a different value of A. Way to move this slider here. It shows you what happens as you change that A parameter. You can change the B parameter. You can also change the C parameter. And you see that it adjusts the location of the roots. You can compute out calculus type information. What is the limiting value as you approach infinity? So what happens as you approach x going to infinity? Well, if you had this quadratic here, it just goes off to infinity. You can also obtain a bunch of information that's useful from a calculus point of view. You can obtain the function overview of this. Gives you functions, domains, ranges, integrals, extremas, et cetera, et cetera. So you can get the global minimum, global maximum. There's this interactive tool that the Wolfram Alpha Map team has created called curve analysis. So you just get all this information on the derivatives. You can plot the integrals. You can hide all these features. You can show one particular part. You can show the integral and the function itself. And then your calculus students, for instance, could figure out, well, as I change information in a function, what happens to my integral? We have similar features and functionalities for trigonometry. So we'll have this notebook published later. I'm not going to go over this particular section today, but I just want to point out you can do all the same activities that we did for polynomials and algebra with trigonometry. You can plot the functions, you can determine your mins and your maxes. You can do complete generality. Again, you can do these manipulatable plots, which is quite useful for determining what happens as I vary a parameter. So what happens as I vary an amplitude? You can make these interactive activities. So I increased A, what happened? You can have your students explore how does the maximum change for a given value of A. And then I just wanted to point out we also have all the Common Core standards, so you can list all those. Common Core standards about fractions. You can, if you know the particular Common Core standard, you can just type that in and you'll get information on that particular standard. You can find out all the algebra standards. And then not only that, but you can type in Common Core fraction examples, evaluate that, and it'll produce in our notebook, and it'll give you a bunch of different activities that you can explore. And it's adjusted by grade level there. And then also with I need to type it with high school algebra as well. So we get that information there. And at this point, I'm going to hand off the talk to Jason here, who's going to talk about how we can get similar information for the chemistry domain.
Thanks, Jordan. So the other thing to remember for the chemists in the audience and other applied sciences, all of the math tools that Jordan highlighted are also available in a Wolfram Alpha Notebook Edition notebook. And so you can blend that right into your chemistry activities as well, particularly the linear fit to experimental data for your classic Beer's Law experiment, or any of the ice table problems in second semester general chemistry will also benefit from being able to use quadratic formula and possibly just use the tools in the notebook as more of a calculator rather than having to worry about various approximations to the quadratic or whatnot. So some of those things can be rolled right into your chemistry classroom, just as it can be rolled into a math classroom. So I'd like to show you some modules that I've built up. These are, we'll start with chemical conversions because they're the center of nearly all the calculations that you have in chemistry. You're moving from mass to moles, things like that. And so we spent a lot of time getting the unit conversion stuff set up in a way that aligns with current pedagogy. And then we'll talk about a couple other examples. And finally, the last one I'd like to show you is how you could structure one of the Wolfram Alpha Notebook Edition notebooks for use in lab. And yes, we will share the notebook after the presentation. We'll put it up into the page for this talk. So chemical conversions, these, if you haven't taken a chemistry class in a little while, look something like this. You know, how much does 5 milliliters of water weigh? So you have to go grab the density and do the conversion from the volume to grams. And what you see right away is that we have the output. Now, just like in the math world, don't know why we're getting those little gray boxes. There we go. Just like in the math world, we have show steps to bring up the step-by-step details of how to solve this sort of problem. And so you can always append show steps to whatever query, chemical conversion query you did, and you'll bring up the step-by-step solutions. As Jordan showed for the math, we have these for chemistry. It starts off with a statement of the problem. And then for the chemical conversions, we immediately start doing the conversions systematically from what you started with, in this case, volume, indicating the standard symbol for volume. And then we set up the unit conversions in a unit dimensional analysis manner and convert from milliliters to cubic centimeters. And then we go grab the conversion factor, which in this case would be the density. And we pull up the value, show, again, specifically for the chemist, what phase of matter and what temperature this was at, because the density changes based on temperature. And so then you multiply using the conversion factor again, and we take the multiplication and set it up in fractional form, the usual fence form, if you will, and bring along the resulting value. So you'll notice as far as sig figs go, since it was 5 milliliters, we assume that the 5 is infinitely precise, and then the limiting factor for significant digits is the number of digits in the density, and that's what's returned in the answer key from the step-by-step results. So we can do a lot more conversions than just volume to mass. We can do mass to moles. And again, here, just to show what these look like, rather than stepping individually through, I'll just show all steps. And so again, just as we did with the volume and density case, we set up the mass, we get the conversion factor, we do the result, and then again, convert at the end from moles to the units that were desired, in this case, millimoles. And so that's taken care of at the end. Now, along the way, you notice in step 3, we had to use the molar mass of iron 2 oxide and, excuse me, iron 3 oxide. And so the student may not remember how to get this value of 159.687 grams per mole. Well, you can just do show steps for the molar mass of that molecule, and it'll go to the knowledge base, grab the molar mass, but then also build an answer key for how to solve this problem. And here we highlight, not only do we have the problem statement up front, but then for properties of molecules like any of the formula masses and some other things, most of the chemistry problems will have the second step to be a plan step, where we lay out a plan for solving these broad category of problems, in this case, the molar mass problems. And this is to align with current pedagogies used in the classroom textbooks, and also to set up the student to think about planning their activities in chemistry, particularly for planning what they're going to do in the lab. As we all know, as chemists, we have to pay attention to what we're doing in lab because we have finite amounts of funding and resources in terms of the solutions or materials that we may have to run our experiments. So we have to plan things out, and that's reflected here all the way back in the classroom with the step-by-step solution. And so what we do is we have the plan, and then we step through it. We go and grab the chemical formula, count the number of elements, number of atoms of each element, and then we go look up that mass from the periodic table, and then we do the multiplication and show the steps out. And again, keeping track of the significant digits based on the precision from the molar masses, or the atomic masses, which of course are then determined by the accuracy in the abundances. We're not limited to just pure substances. We can have solutions. In this case, we have an example of a single component solution where we have an aliquot, and we want to know how many molecules of magnesium hydroxide there are. Nope, it seems to have misinterpreted that. That's unfortunate. I have to check that out, see what bug is crept in. We can do components, so how much carbon is in 5 grams of sucrose. That will then go and pull up the Wolfram function repository function chemical element composition. And then notice for chemists, we often have a very tight curriculum, whether you're in college or high school or possibly even grade school. And so being able to show computations and conversions of natural language queries, the things that we're talking about in classroom or in a real world environment, and converting that into Wolfram language that we could programmatically do. One of the aspects of Wayne that I think is very important is that it converts this into the language here. And so if you want, and if you're looking to bring that component into your classroom of a little bit of programming, you have it right at your fingertips here. If for whatever reason you're not interested in doing that, you can hide that. You have the ability to hide some of that away under the options over here. You can hide the Wolfram language inputs. So you can just have query answer if you want, depending on where your students are in the particular curriculum that you're working in. Lastly, the other one that I wanted to show as a highlight of the conversions that we can do, you can do concentration conversions. Currently, we don't have step-by-steps for that. They're in the works, so check back. Hopefully in a couple months, they'll be there as they roll out through the Wolfram Alpha site. So that was how to do some conversions. And you can see how you could structure activities, but to help drive home how those activities might look like, I wanted to show you some examples that I had built. And so we'll go to the average atomic mass, which this is a query that you can't do in just one computation. You need to do a couple steps because you first have to go get information and then you have to manipulate it. And so here we have the layout of problem statement of what you're going to do, compute the average atomic mass for silicon. And then in gray, we have the steps that the student would potentially be working through, either as an example, or maybe, as I'll show in a moment, something where they're responding to an activity, either a group work or individual assessment. So here we can just ask for the property that we need, and we get back an association with the values. Now here I've chosen to show how we could take these percentages and manually convert them back to decimals. You don't have to do it this way. There are other ways of doing it, but I just wanted to show that we could set 3 different variables all in the same input field. Now note that only the last one gets shown, but you can set all 3 of these variables. And let's see. Yeah, and so what you see in the output here is that you set 3 variables A, B, and C, and now those can be then used in the next calculation. So this is where a little bit of the programming might come in. And so if your students haven't had any exposure to that, you might, this would be a nice way to slowly introduce them to that. And then we can just plug everything in and mix our use of variables, which hold values that we previously found, with other natural language. So we're going to ask for the atomic mass of each of the 3 isotopes and multiply it by its abundance. We can show that in real time if you like. And again, it converts it into the natural language into the Wolfram language input, shows it there, then gets the results. And since the atomic masses are stored in the knowledge base, we can always check that against what's stored and what we computed. And then, of course, as a good programmer, you just want to clear your variables so that if the student happened to use things later, they didn't clobber each other from previous activities. Now, one of the most difficult things for particularly new students coming to chemistry is visualizing molecules, and the structure and seeing things in 3D is challenging for many folks. And so we can work with tools that are in the language and that are available through the notebook here to investigate that. So here we start off with just a chemical formula, not giving it a name, not showing it any structure, and just we could start by the activity, how many atoms are there? So you're learning to take the number of, read the subscripts and everything and compute the total number of atoms. And there's step-by-steps for this as well, but I'm not going to show that at the moment. Then you can progress from counting number of atoms to thinking about percentages, mass percent. And so then you could ask about that. And again, we do have steps for the mass percent. You should just show steps mass percent, and it'll walk you through that. But then you can move from thinking about the information from the structural, just the formula, to start moving to the structure of the molecule. And here we've introduced that caffeine is a molecule with this particular chemical formula, and we can ask what that looks like. And so one can just say caffeine Lewis structure and get the results here. Now the Wayne knows that we have step-by-steps for this. We have a natural language representation of the Lewis structure. So you can just click the button and it'll build the show steps input for you. And so you can get access to that. But again, if Wayne doesn't yet know, or if we don't yet have a natural Wolfram language interpretation for the particular property that you're after, you might just do the show steps by hand. To find out what new chemistry representations we're going to have in the language, I would encourage you to attend the 11 o'clock talk tomorrow by my colleague, Jason Biggs, where he'll be espousing all the different new functionality that we have coming in version 13 for chemistry. So hopefully you'll see more, well, in the future, you'll see more step-by-steps automatically suggested as we have representations for different things. So we can look at the Lewis structure diagram and then have the student compare that to just a standard structure diagram using the more organic notation where the hydrogens are elided. We can ask them to think about that and provide a response in this, in this cell here, just highlight and type in their response. Then you can ask about the 3-dimensional structure. And one of my favorite phrases, I just need a molecule plot of X. And here I wanted caffeine. And so we get 3D rotatable molecule plots. So this can be very helpful to be able to see the structure in 2D and 3D side by side. And we actually have a function repository function that will do that. It will set the two structures side by side, and you can get that from the Wolfram function repository. And again, you can rotate and see the structure with and without hydrogens, and you can move the 3D to a different representation. You can get access to that same sort of stuff here in the notebook as well. Just ask for the stick plot and the space filling plot, and you can compare them between the different representations and ask your students to think about that and put information into their notebook. Moving on to a more complicated calculation is the reaction enthalpy. So here we're going to use the bond energy approximation to estimate delta H of reaction. And again, the power of the Wayne notebook comes in, that you can just balance the chemical equation and it'll do the balancing. Again, if you wanted to see the steps on how to do the balancing, show steps plus this expression will immediately bring that up. Then you can immediately bring up the Lewis structure for the series of reactants and products in your reaction of interest. And so now you've got the bits that you need to be able to see which bonds are breaking and forming just in 2 lines of query in your notebook. And again, the power of the natural language comes in that we have a large tabulation of bond energies in the knowledge base. And so you can just request the bond energy that you want and do math with it right off the bat. Much like we would introduce the concept of how to use these bond energies in the classroom. So we can figure out which ones break, which ones form, add those together. Now, a little bit of the language syntax. Penultimate is this, the second to last output, and last obviously is this one. And so you can use that terminology just to do the division, or excuse me, the subtraction. You could equally set the previous values to variables and then do that here. But the penultimate result and last result can be kind of fun to use as well. And again, we have the experimental results stored in the database, so you can ask for that and then have conversations about, negative 130 versus negative 136.4. Where did the 6 kilojoules per mole of energy go, and dive deep into the chemical thinking of that with your students. One of the things that I'd like to show now is moving from just sort of group work or classroom activities, or possibly homework assignments that are done in a remote environment, is to moving towards something bigger, not just problem solving, but actually doing data analysis and data collection that one would have in a laboratory environment. Now, as you have seen, you can put lots of text around your inputs, and that really sets up the notebooks to be able to do laboratory activities. Now, I have put together an analysis of vinegar experiment that we used to do in my laboratory. And what I have done is I've omitted some of the bits that would normally be in the handout for the activity. But let me just walk you through that. So again, if you're starting to move things online or into an electronic format, I highly recommend that you have an academic integrity statement where the student has to enter their name and acknowledge that they've thought about what they're allowed to do, who they're allowed to work with, and understand the assignment. Put that up front. Then presumably you would have some sort of possibly a pre-lab activity. I've not put one here, but you can imagine if you're, in this case, we're going to use the set precision function. So you would imagine that maybe in a pre-lab, you'd have a little practice with using the set precision. Maybe it's have the student go to the user manual and just read a little bit about what set precision does. You would also probably have questions, chemical thinking questions about acids and bases, and just some laboratory activities that they might be doing for the first time, the techniques. That easily can be dropped in, along with the full step-by-step instructions for what you're doing. Like I said, I omitted that for clarity so that we could highlight here, not so much the text of the activity, but rather how we can change the way we collect the data, interact with it, and then build the answers that the students would potentially turn in a report or even just turn in their notebook, having completed the laboratory experiment. So I'm going to move to the data collection bit, and this is where I wanted to point out that, again, if you're going to have a large number of students doing this activity that you or others might be grading, it's really important to hone the instructions such that common variables are used and that things are very explicit, so that students don't wander too much. It gives a strong framework of scaffolding to make things smooth for them and also smooth for you for the grading. So here, where we're going to record the tightened concentration in the particular units that we want, reminding them to use set precision and giving them the name of the variable that we want them to use. And so then it just becomes set by similarity and the precision. Now, if you haven't worried about precision in Wolfram Language before, set precision is one of the ways to set the number of significant digits. And we can combine that right with the units, and you'll notice that it's immediately parsed all together. Then we would then go and collect the different acid volumes in milliliters. And again, we can create a list and we can do a conversion all in one fell swoop. So we can put in our milliliters, convert that to liters, and set the precision. And that's carried right through all in one. Now, again, if the students haven't done a lot of programming or worked with maybe a spreadsheet program, we would want to introduce them to this notion of a list, and that we're just tabulating multiple pieces of data that then are going to be operated on as a group. So that might be the new thing, moving from a pencil and paper doing each data point at a time, that we can skip over because now we can have it as a list. We'd also collect the initial Biuret readings and the final Biuret readings, and that would be all the information that we needed for this titration experiment, where we're trying to confirm the concentration of acetic acid in vinegar. So then we get to the data analysis. And the nice thing about having things stored as variables is then we can use them in further calculations below, and we can have our data collection and our data analysis all in the same notebook side by side. Again, since we've given instructions of which variables to use, we can immediately start using them again and set the results equal to new variables. And you'll notice that the units are carried through just as we would do in the classroom, and we can multiply things together, keeping track of significant digits. And note that when you take a milliliter kinds of concentration, we get just the moles, and that is all done in the background. So if you're presumably at this point in the students' progress through the course, they would have already shown mastery of doing the unit conversions, and we can then let the computer do it. If not, then you might have the activity structured slightly differently, where they're showing how to do each of those bits to prove that they've learned that concept as well. Then we can compute the acid concentration. We get our three values, and then get the average of that, which then returns in machine precision. So you just have to ask the students to think again about significant digits. And we look up the density. Now, acetic acid is a solution for which we have quite a bit of data in the knowledge base. Not every single component solution you can envision is there, but a good number of them are. And so here we set the precision of the molarity for our solution and ask for the density. And then we can either have the system do the conversion, because it will convert, as I showed before, concentrations, and it can go from molarity into mass percent, or you could have your student ask them to work out the steps along the way, depending on, again, where they are in the curriculum and what is being assessed in the activity. And again, here's a space for them to put out their response to the built-in question and thinking about things. And then again, clearing the variables used, so that if they're doing further work down on in the notebook, that they have they don't have leftover data hanging around in the system. So I hope that these series of chemistry modules give you some ideas of how the Wolfram Alpha Notebook Edition could be rolled into both your learning space and your laboratory space where education is going on, and how possibly the notebook could facilitate an easier way of data analysis and possibly an easier way of grading. You could also envision that if you happen to have to be in a remote environment again, then data could be provided in the notebook and the students could work on this at home, still doing the data processing rather than if they didn't have the opportunity to do the actual titration experiment in a laboratory environment for one reason or another. Lastly, before we go on, I just wanted to point out that there are, through the Wolfram Alpha Notebook Edition, we have new buttons at the top that allow easy access to our interactive demonstrations, for which there are quite a few for chemistry. So if you click on the physical sciences and bring up the new notebook, you can go over to chemistry. And we have a slew of different notebooks, different demonstrations that can be used on various topics. Here's Vesper and a variety of other things. There's a lovely titration experiment that's a little further into the collection that if you do have to do a titration experiment remote, you can have the students interact with that demonstration. But those can all be brought right into the new notebook brought up, and you can put that into the notebook that you provide them, or have them just interact with it on their own. Besides the interactive demonstrations for chemistry, there are also the starting point notebooks. And so these are examples, much like many of the examples that I have here. And so in the chemistry domain, we have 8 notebooks worth of topical content. So there are about 150 or so examples in this collection showing you how to do various topics and elements, equilibrium, mixtures. Again, more places for both you and your students to see how the tool can be used in a chemistry environment and how activities could be built up for the student to interact with. And lastly, before I finish, one of the things that I did want to show is how this Wolfram Alpha Notebook Edition can combine with our cloud technologies. And I'd like to scroll back up. Sorry for the fast scrolling. Now, as I said before, visualization is one of the things that can be a big sticking point for many new students of chemistry. And so I can bring up a new notebook, and if your institution doesn't have a pile of MollyMod kits or other molecular modeling kits, having the ability for students to be able to look at a particular molecule or series of molecules at home while they're reading their textbook or otherwise processing an activity that you've assigned them can be very helpful. And so with our cloud features, we can just cut and paste. I'm going to cut and paste this into a new notebook and then immediately go up to the file menu and publish to the cloud. And so that brings up a new dialog, and I'm going to call this WTC demo. And I'm going to allow access to everyone. Hit publish. And while it thinks, I'm going to copy the URL. And now I can go over into a new tab in my notebook and bring up the cloud version of this, which then your students can pull up on their device, pull up on any of their mobile devices or their laptop at home, and immediately start. Oh, lovely. For some reason, the loading took a moment. But they can get access to the molecule of your interest, and so you can provide essentially a virtual molecular modeling kit for them to access from home. And like I said, when the cloud is not misbehaving, you can immediately interact and rotate in 3D and build activities that would be able to question and critically think deep about that ability at home. So with that, I will stop. And I'd just like to bring your attention to the other talks going on tomorrow that further showed other features of our Wolfram Alpha Notebook Edition. So there's what's new in the Notebook Edition starting Friday at 9 a.m. Central Time, and then interactive plot quizzes. That's this other button up here that I didn't explain and show to you. So we have a lovely talk about that at 10 o'clock, and then the health, nutrition, and fitness we'll be talking about those topics in a Wolfram Alpha Notebook edition tomorrow at noon. So with that, Jordan and I would be happy to take any questions that you might have. Feel free to type them into the Pathable chat, and we'll answer any questions you might have. And as soon as we finish, we'll post the notebook to the presentation in Pathable.
While waiting on questions, I was going to share the screen real quick here. I just wanted to point out what Jason was talking about a moment ago. That we have these interactive plot quizzes here. So far we've created ones on plotting curves, building functions, calculus concepts, and understanding data. And there'll be more along the way, which Jeremy and Anne-Marie will be talking about tomorrow. If you click on one of these, for instance, you can generate a linear regression data quiz. So you want to generate a set of 7 points that exhibit a linear regression approximating x plus 5 with a given goodness of fit. And so you can interact with these and get various quizzes here. So I just wanted to point that out. And again, that talk is at 10 to 10:30 tomorrow. And then, as Jason mentioned, also finding out new information at 9 to 9:30, and this one on health and nutrition at 12 to 12:30. There's a question here. So where will we see notebook capabilities 5 years from now? From the notebook edition, we're continuing to add and implement new features. So we have been working on things like the interactive plotting quizzes and trying to create interactive visualizations, which you'll be able to hear more about that tomorrow. Brad and Stephen tomorrow will be talking about some other new features that are coming up, we'll continue. We're continuously adding various natural language inputs such as we've done here. Jason, did you have any more to add on that?
Yeah, from the chemistry side, we're hoping to have step-by-step support for all the chemistry, for everything that has a representation in the Wolfram language. So the most notable ones that are missing at the moment are pH calculations, ice table sort of calculations, those equilibrium problems. So that's the next big push that we're working on, both to get a representation in the language and get step-by-step support for on Alpha and in the notebook. And so the hope is that we would be in 5 years from now, at least from the chemistry side, that you would be able to use a Wayne notebook to do natural language for everything that you would want to do in a first-year curriculum or an introductory high school, middle school sort of science curriculum that's chemistry related. And we're hoping to get towards chemical reactions, doing both balancing, not just balancing and stoichiometry, but possibly even doing more with actual synthetic reactions. So it'll be interesting. Any other questions before we head out? Well, thank you for attending and have a great rest of your conference. And we'll post the notebook in just a moment. Bye now.